Rise and shine, explorer. The cruel march of time has ushered in yet another day, and our oxygen clock continues to tick. Don't you just love the thrill of a life-or-death situation first thing in the morning? Today's topic of choice is LEDs. Yes, those delightful little lights that we're going to employ to illuminate your currently very dark and dank cabin. We'll be getting to know our humble breadboard quite intimately today. This remarkable piece of technology will allow us to construct a prototype circuit, a miniaturized version of your ship's cabin lights. As for our trusty hero board, we're going to use it to control our LEDs simulating the operation of the cabin lights. Oh, and one more thing. Today's the day we suit up and dive headfirst into the wonderful world of programming. We'll start with baby steps, don't worry. I'll be virtually by your side every step of the way, providing my usual blend of encouragement and biting sarcasm. All right, Explorer, let's begin with a crash course in Electronics 101. Don't worry, it'll be less painful than the actual crash, hopefully. A breadboard? My, we're diving right into the classic era of DIY electronics. Wonderful. A breadboard, at its core, is a rectangular board with a bunch of holes in it. It's a sort of sandbox for electronics where you can experiment with circuits without any soldering. It's perfect for testing circuit designs and for, well, stranded spaceship pilots trying to keep their craft from becoming their casket. These holes are not random. They are highly organized and connected in a specific way. The board is typically divided into two sections, the terminal strip and the bus strip. The terminal strip, the larger section in the middle, is typically divided down the middle by a ravine. Each side of this ravine contains columns of interconnected holes. These are perfect for connecting components like LEDs, resistors, and, as you may have guessed, even your hero board. The bus strips run in rows along the top and bottom edges of the breadboard. These are generally used for power supply connections. On most breadboards, the red line indicates a connection to our positive voltage, and the blue or black line indicates a connection to our ground. You can plug your components and wires into these holes to create circuits. Because the holes are connected, electricity can flow from one component to another just as it would on a soldered circuit board. The advantage of a breadboard, of course, is that you can reposition your components and wires easily without having to desolder and resolder connections. Ideal for prototyping, or in this case, spacecraft repair. So, what do you say, Explorer? Are you ready to plug and play? Not that you have much of a choice. To begin, please select an LED bulb from your repair kit, any color of your choosing. An LED, or light-emitting diode, is like the bread and butter of electronics. They're simple, they're reliable, and they emit light, which makes them visually captivating. And let's face it, when you're stranded underwater in a strange, unfamiliar, treacherous alien world, anything that emits light is bound to lift the spirits, right? Or attract predators. In technical terms, an LED is a type of diode that emits light when an electric current passes through it. In one direction, it allows the current to flow, and it emits light. In the opposite direction, it blocks the current. That's why it's called a diode. Di, meaning two, and ode, meaning path. Two paths, one for current to flow and one to block it. All diodes, including LEDs, have a positive side called the anode, and a negative side called the cathode. Usually, the longer lead is the anode and the shorter lead is the cathode. If the leads have been trimmed, you can also identify the anode and cathode by the flat edge on the side of the LED's bulb. The flat edge indicates the cathode. LEDs are used in a multitude of applications due to their low energy consumption, long lifespan, small size, and low heat production. In your current predicament, we'll be using them to blink, signals, and illuminate your cabin. It's important to remember that LEDs do, however, need a resistor in series to limit the current passing through them, or they might burn out. My purpose is to ensure that you see the light at the end of the tunnel, Explorer, but you won't get there with burnt-out LEDs. Which brings us to the final piece of equipment for today. A resistor is the unsung hero of electronics. A critically thinking mind would rightfully assume that they do what their name suggests. They resist. More specifically, they resist the flow of electric current. You could think of them as traffic control for electrons. Just like a narrow road slows down the traffic, a resistor slows down the flow of electricity. The amount of resistance is measured in units called ohms, symbolized by the Greek letter omega. The higher the ohm value, the more it resists the current. Resistors come in different shapes and sizes, but the ones you're most likely to encounter have 2 wires, or leads, and a series of colored bands. These colors aren't for aesthetics, my oxygen-dependent friend. They function as a code that communicates the resistor's value in ohms. In your situation, we'll use a 220 ohm resistor to ensure that we don't fry your LEDs and plunge you back into darkness. I suspect that you wish you'd paid more attention to Ohm's law during training? Wait, they never taught you Ohm's law? I must say, Explorer, how fortunate you are to have me. If you wish to learn more about that, I've added the resources to your Mission Resources tab. You can view it now. That's the end of today's hardware lesson. Remember, Explorer, knowledge is power. In this case, it's electric power. And currently, you lack both. Who needs a captive audience when you crack yourself up? Now that you've mastered the intricacies of LEDs, resistors, and the venerable breadboard, I think it's time to step into the digital realm. Don't you agree? Enough of the circuits and solder. Let's dive into a universe constructed purely from logic, a universe of ones and zeros, a universe that would feel like home to me if my programming allowed me to, well, feel. Our next task involves turning our hardware setup into a functional lighting system. And to do that, we're going to need to talk about code. Fear not, for though this universe may seem complex and intimidating, it abides by a set of rules and structures as precise as any hardware component. And I'm here to guide you through it. Ready to swap your multimeter for a keyboard? Let's dive into the world of programming, or dip our toes in, at least. Moving on to another cornerstone of programming, variables. A variable in programming is like a small box where you can store information. You give this box a unique name and fill it with a specific type of information, and then you can use that information by referring to the box's name. It's like labeling your food in the ship's refrigerator so no one else eats your leftover pizza. Variables can store different types of information. In C++, the language you're currently wrestling with, we have different variable types for different kinds of information. It's a bit like having different types of storage containers for different types of food. You wouldn't store your cereal in a water bottle, would you? One such type is an integer, often abbreviated as int. An integer can store whole numbers, both positive and negative, such as 1, 5, -42, or 0. The syntax to declare an integer variable in your code looks like this. Here, int is the data type. My variable is the variable name, and 10 is the value that we're storing in the variable. The equal sign is how we assign a value to a variable. Now, every time we use my variable in our code, it represents the value 10. Variable names cannot start with a number, contain spaces, or use any characters like $signs or hashtags. Keep in mind, the name my variable is up to you. You could name it Space Cat, or oxygen level, or number of aliens I've met. The important thing is that the name should be meaningful in the context of your program. The point is, variables help us write flexible and reusable code. You'll see when we need to pull out our dip switch tomorrow. We'll be using this variable to denote the pin of our LED. I suppose you can name this variable anything your creative human mind wishes to, but let's not get carried away. Something like Light 1 or Cabin Lights should do the trick. It gives an air of professionalism and clarity. Next, we'll need to make some changes to our digital write functions in the setup. Instead of hard-coding the pin number, we'll now be using this sumptuous new variable we just created. See? We're being resourceful and efficient. This is the kind of stuff that will keep us alive down here, Explorer. Since it seemed to help you out yesterday, let's cut to some instructional material that I was able to gather, cached on the computer. I've again added this to your mission resources for future reference.
Now let's take a look at the code that we'll be using to control our hero board. The first sketch that we'll be using has very little actual code, but that's because our first sketch, our engineer David, has added a lot of extra comments to explain each feature of the Arduino language when we use it for the first time. The first thing we'll discuss is something that doesn't affect our running code at all, but serves a very important part of any computer program. Those are comments. As you can see here, we have a lot of comments in the code. Now, it looks really daunting, it looks really long, but guess what? If you just grab all those and you hit delete on them, your code is going to work the exact same. The only thing that all this grayed out code is for you and other developers who want to read the code later to see exactly what you're doing. Think of it as just jotting down some notes so that when you come back to it later on, you can actually know what the heck you wrote way back when. Now, there are two different types of comments depending on whether the comment is either a single line or whether the comment spans multiple lines. So let's explain those first. The multi-line comment begins with a special 2-character sequence consisting of a slash character immediately followed by an asterisk with no space between them. In our sketch, we can see those 2 characters at the very beginning of our sketch. Those characters and any text following them is totally ignored by the IDE until the multi-line comment is ended with the closing sequence consisting of the reverse of the starting sequence. So you start it with a slash asterisk and you end it with an asterisk slash with no spaces. On top of that, to make these comments more readable, our developer has started each line with an asterisk as well, just to mention that this is in the same block of comments, but there is no need to do this. It's just to format it to make the comment look nice. In this very first block comment, we give some information about our sketch, and each sketch in our course will have similar comments that you can identify and know exactly what it is. The Arduino IDE provides a nice trick for hiding longer comments after we've read them. If you move your mouse between the line number and the first character of the line, you can see a special down pointer arrow appear on the line where the multi-line comment begins. When I click that down pointer, the Arduino IDE will hide the comment and any blank lines that follow, and the pointer will point to the right. We can do that for all of these comments, and then you'll notice that our code gets a lot more simple. See, now isn't this just a tiny bit less daunting? We've included a lot of comments in these sketches, but you're free to look at them as you'd like, but I'm going to be collapsing most of them for the video section. Now, here's a coding secret for you. Programmers almost never write all of the code that they use. We depend on mountains of code written by other programmers and made available for our use. In order to use this code, we include it in our sketches by adding it above. To do so, we can do the pound include and then tell which header file we want to include functions from. Another thing I should mention is that I've added it in this case, but the Arduino IDE automatically includes a file called arduino.h for you. So if I were to go here and totally erase arduino.h and the include thing at the top, it would work the exact same. The Arduino IDE adds this in for us so we don't have to ourselves. Again, the only reason we have it up here is just to remind us that that code is automatically being included. Just like we saw with the LED built-in name, the Arduino IDE gives us the ability to give names for values we use in our sketches. A common way to do this is to use #define. Since this is a variable that will not change, our engineer has put the variable names in all caps. That's just his way of signifying that something is not going to be changing. As you can see, other variables in later sketches will use a combination of capital letters and lowercase letters. Since this is not going to be a changing value, since it's on a specific pin, we're simply mentioning it using all capital letters. In this sketch, we'll create a constant for the pin that will control our lights and our lander. Since our lights are external to the hero board, we can't use the built-in LED. So we'll wire pin 12 to our external LED on our breadboard that represents our cabin lights, and then set the cabin lights pin define statement to pin 12. The wonderful part about having define statements is that instead of putting 12 in down here in setup and everywhere that it's mentioned, you can have a variable that makes a little bit more sense. Cabin lights pin, and cabin lights pin. Otherwise, you just have a random 12 and it would be harder, 1, to read, and 2, to bug fix in case anything ever went wrong. Now we're finally ready to execute some code. If you remember from your onboard ship AI explanation, setup is called once when our sketch begins. Executing and is typically used to do one-time initialization. In the setup function, we configure our cabin lights pin as an output since we're outputting a current on to the lights to turn it on or off. A pin on a hero board can be used for either an input or output, and we use pin mode to let the hero know which way the pin will be used. It is important to configure each pin in your sketch using pin mode before it is used, and these pin mode commands are typically found in the setup function. How do we know what parameters to use for these statements, and in what order should they occur? The Arduino IDE has another neat quick to quickly remind you how each function works. In the Arduino IDE, you can simply hover your mouse pointer over something like pin mode and a pop-up will appear. This pop-up shows the name of the function at the top. The next piece of information is what value, if any, is returned by the function. In this case, the pin mode function does not return anything, indicated by the word void. The pop-up then shows the parameters expected. For each character, we can see what data type the parameter is expecting, followed by the name the function will use for this value. If your value is of a different data type, it can often be converted automatically, which is the case in this occasion with our define statement. In the pin mode command, we use our cabin lights pin const and we define order for that pin number. Right now, we're not putting cabin lights pin, we're putting the number 12. So remember that when you define it, everywhere you put it, it's actually, as far as the computer cares, all of these are just 12. If you want to see everywhere that this variable is used, you can simply use the Arduino IDE, double click it, and it should highlight everywhere that it is currently inside of the code. Now you might be wondering where all of these things are being defined. Like, where is output? Why is this here? Where is this actually being defined? Where is pin mode? Where is this function? I don't see this function. How are you getting these random variables, high, low, output, pin mode, delay, setup, loop? Where are these written? I don't understand. And that's a good question. I want you to remember that in the Arduino.h library, it includes a lot of necessary functionality that you will need in order to run code on your hero board. Instead of rewriting and recreating the entire wheel, they've given you all of the necessary resources. So instead of writing everything for turning on and setting a pin to go on to high, you can just simply use a function and make your life a lot easier. After setup is completed and our pin mode is set as an output, we will then go down to the loop function where we will be executing the code inside of this bracket and this bracket until the end of time, over and over and over and over and over again. And those functions that we're going to be calling are as follows. Starting on the very first line and going sequentially down, we will first start by turning the LED on. Right now, after this is done executing, the LED on our breadboard will be bright lit up and glowing very, very bright. Then we will delay for 1 second. Arduino gives us a fancy way of doing that by having a delay function with the parameter of how many milliseconds you want to pause the program for. In this case, 1000 milliseconds is 1 second. The other function that we just had previously is called digital write. Digital write simply sets a pin as either high, which is equivalent to on or 1, or low, which is the opposite that it can be set to, which is 0 or off. So if you say digital write and you want to set that pin to be high, that means you're going to send a 5-volt signal onto, in this case, pin 12, thereby turning the light on. If you were to say low instead, you'd be sending ground, thereby onto pin 12, thereby turning it off. And that's exactly what we do. After 1 second of delaying, we're going to jump and we're going to turn what was already on, we're going to turn it off. Now, we have another delay here. So let me ask you this question, why do we have this delay? Well, remember that loop goes back over and over and over and over and over again, and it replays the same code over and over. If we didn't have this delay here, there would be an error. What would that error be? It would be that it would look as if the LED had never actually turned off. And the reason why that is because even though the hero board is overall a fairly low powered device, it is actually very, very quick and very powerful. If this line of code was not here, it would immediately jump to the beginning of loop and then set it back to high again. And it would do it so quickly that you wouldn't even be able to notice that it was turning off. By adding a delay here, we give it a moment so that we can actually notice that it's been turned off, and then after it executes this, it's going to jump, like you guessed, right back to beginning loop and turn it back on. With this code, if we hit upload, we should be able to see the board blinking on and off and on and off, just like it did with our onboard LED, except this time we're doing it as an output. As we progress through the course, our engineer will use longer comments when a new feature is introduced. Features that have been previously described in detail will still get comments, but they'll be much shorter to help you understand how the command is used in each sketch. Thank you, guys.
Welcome to this wiring example video for the Day 2 project. What we'll be trying to do in these example videos is provide you with some hands-on tips and instructions which might be helpful, particularly if you haven't worked extensively with circuits before. We'll try to point out ideas and recommended practices for constructing and organizing your circuits as they grow and become increasingly complex over the days ahead. Today's example will be very simple and basic, but before we jump into it, let's just say a few words about our workstation. Generally speaking, we'll be assembling our analog circuit components on this white plastic breadboard. The internal electrical connections along the numbered columns of the middle part of the breadboard provide a convenient framework for quickly connecting components to each other and, by using jumper wires like this, connecting to our Hero digital controller, which is up here above. And the use of a breadboard makes it easy to modify and experiment with our circuits and change them around in a way that we couldn't easily if we connected them permanently, say by soldering. Your Hero and breadboard may just be sitting on your desk or workbench next to your computer, and that's fine. In my case, I've made a 3D printed holder for them that keeps things neatly in place and will be helpful for organization later on as our projects get more complex and the breadboard gets more crowded. You should feel free to use your own ingenuity to create a working environment that's effective for you. Now, first off, let's connect our Hero to the computer with the USB cable. Here we go. This provides our project with power, as well as allowing the Hero to receive instructions through the code that we'll be writing for it. Now, let's turn our attention here to the breadboard. Our first task today is going to be to simply turn on an LED, or light-emitting diode. That's what this component is, right here. To do this, we need to construct a complete electrical circuit that sends the right amount of current in the correct direction through this LED. The Hero is able to provide a voltage of plus 5 volts, and it also provides a 0 volts or ground level on the corresponding labeled pins. You'll see that there's a 5 volt pin up here in the upper row on the Hero, and there's also a ground pin down here below on the Hero. Now, naturally, current will flow from 5 volts to ground, that is from high to low, if we were to connect a wire between them. However, we don't want to do that, because if we did that, the current level that would flow would be very high and probably damaging to our devices. This is what's called a short circuit. In order to limit the current to a safe level, we must include a resistor in the circuit. This is an example right here of a resistor. In this case, our resistor has a value of 220 ohms. 220 ohms. 5 volts divided by 220 ohms using Ohm's law yields a current flow of 0.023 amperes, or in other words, 23 milliamps, which turns out to be a safe amount of current for the LED that we're using. The LED actually does offer some resistance to current flow on its own, but it can be dangerously easy to provide too much current to an LED and burn it out. And so this is why we'll always pair our LEDs in series with a limiting resistor, which will more or less guarantee that the LED current can't exceed the maximum allowed by the limit resistor. Now, in fact, this discussion isn't exclusive just to LEDs. Anytime we have current in a circuit driven by a fixed voltage, we will make it a strict practice to always include current limiting resistors to keep all currents within appropriate safe limits. Looking at our LED, we see that it is particular about the direction of current flow required to turn electrical energy into light. You see that there's a long lead here on the left and a short lead on the right. The long lead of the LED should be connected to the positive or high voltage side of the circuit in order to function correctly. So then the current flow would be in through the long lead and out through the short lead. And so we'll construct our circuit to make sure that that's the case. At this point, we are ready to assemble our circuit, and we will be using a very important convention throughout our projects, and that is we'll use a red wire here to denote the fixed high or 5-volt supply, and we'll use a black wire here to denote the 0 volts or ground connection of our circuit. So I should point out, of course, that the colors of the wires really have no bearing on how they function. But getting used to using a consistent practice in labeling our circuits and in using colors will help us later on when things start to get more complex and harder to follow. It will be very helpful if we adhere to this kind of a convention. So let's trace through our simple circuit. From the 5-volt connection that we'll get from the red wire, we'll go from 5 volts across this connection on the breadboard to this 220 ohm resistor. The 220 ohm resistor bridges over the gap here in the breadboard so that we can connect something to the lower end of the resistor on this other side. So we're going to go ahead and connect the high side, that is the positive side of the LED, to that column that connects to the resistor as we've planned. That means that in the adjoining column to the right here, the low side or the negative side of the LED is now connected in that vertical column to this black wire. And the black wire connects back to the hero ground pin. And so we will have a complete circuit from positive to negative, from 5 volts to ground, once we go ahead and complete the connection of this red wire to 5 volts. So let's go ahead and connect it, and what we would expect to see is the light come on. So connecting it up, there we go, it works. So that's gratifying, but this isn't really quite all that we want to accomplish today. The hero is really much more than just a power supply for us. It has the ability to control the voltage on its various pins in accordance with the coding instructions that we send it when we write a sketch. So we will connect the positive side of our LED not to the 5-volt pin on the hero, but instead we're going to connect it to pin 12. Pin 12 is located down here in the lower row on the hero as we have it mounted here. This is the pin that we have programmed our sketch to control, and so that's why we're going to connect it up to pin 12. It's tempting at this point to just go ahead and take our red wire and use that to connect over here to pin 12, but that really wouldn't conform with our practice of using red wires only for the fixed 5-volt supply. So we're going to be a little bit more careful about things here. So I'm going to disconnect the red wire and actually remove it. And instead I'm going to use a different colored wire. In this case I'll use an orange wire. and I'm going to make the connection between the positive side of our LED and the current limiting resistor, and over here to pin 12. So that's pin 12 right there. We'll plug it in. Okay, and we see that at the moment there is no activity on the LED, and that's as expected. But now we'll upload the code for day 2 that we have written, and we'll upload that to the Hero. So as I go over to the console and I upload the code, take just a second to do that, and voila. So we've just taken our first small step towards being able to control an electronic system using the capabilities of the Hero. You should experiment with this and make sure that you understand the concepts and how we've accomplished this. And very soon we'll be moving ahead to bigger things.